then I think I'm going to try to do it so that it's not very formal, but hopefully also not very disorganized. So, all right. So let me here. I'm going to draw something, which is kind of looks very simple. And so let me kind of elaborate a bit. So somehow here, what I want you to think is that there is somehow I was given some Fuchsian group, kind of in the behind the curtains, let's say, and somehow I was able to compute a fundamental domain, which I think somehow even a Dirichlet domain. And that's what you're seeing, somehow the Dirichlet domain of certain Fuchsian group that somehow I know which Fuchsian group it is, but somehow I'm not telling you explicitly. I'm not showing you the Fuchsian group, right? So somehow we are only seeing somehow this combinatorial information. And what happens here is that the Fuchsian group has a Mobius transformation that sends the blue geodesic, the blue shortest curve, in this blue one onto this blue one, and the yellow or orange one, the other one, into this other one. Yeah, I don't know which color you see it. Well, I see it here like somehow like orange, but anyway. But it's you see somehow this if you so okay, so let me be more specific. So actually it's not any Mobius transformation that sends the blue in the blue and the orange in the orange. It's two specific ones, and the blue one actually sends this point at infinity into this point at infinity, this point at infinity to this point at infinity, and actually what is the Euclidean middle point here into the Euclidean middle point here. So it's like a very specific Mobius transformation, right? And since I'm telling you what it does in 3 points here, it's fully determined by that behavior. And the orange one has the similar behavior. So this point goes to this point under the orange one. This point goes to this point, and the middle point goes precisely to the middle point here. And by middle I mean the middle, the Euclidean point. Right. And now it turns out that this Mobius transformation under inverses, right? Because if I have the one that sends this one to this one, of course I have the inverse that now sends this one to this one, right? And correspondingly also for in the orange situation. And this turned out to be precisely the elements of the Fuchsian group with the property that gamma of d bar intersects d bar. I mean that somehow you have to believe me kind of just as a dogma, right? I mean, it's kind of you just have to believe me that it has the property, and as a consequence, what happens is that those Mobius transformations, which are just 1 and its inverse, 2 and its inverse, so these 4 Mobius transformations generate the whole group. And then what happens that for instance, let me then apply the Mobius transformation that sends this one to this one and see the image, right? So what you are seeing here is the image of D, of the blue one, of the blue fundamental domain. It's another fundamental domain. And actually the kind of the way you should think about it is that somehow this whole thing, so maybe let me do it here. So somehow this thing moves. You see, it's kind of, it's not that it's reflected, it's that it really just moves. The whole thing moves in that direction. So maybe it's easier to show it. Now I apply this other one, which what I did was just apply the Mobius transformation that sends this one to this one, and so what happens is that this just moves here. Right? So this one goes to this one, right? And with the orientation that, for instance, if I traverse this one in this direction, then the image is traversed in the in the corresponding direction, and so on, right? And now I can, well, let me do it kind of for the generators. Right? So those are the images under those Mobius transformations. But now let's see here. Here now what I have is another fundamental domain. And now what it turns out is that now I have a Mobius transformation in the Fuchsian group that sends the blue one onto the blue one and the orange one onto the orange one. And it lives in the group. So somehow the point is, then one should be able to express, for instance, the one that sends this blue one onto this blue one in terms of the four generators. Right? So let's see what happens. So this one goes to this one, and so what can I do? I can apply. You see, I can just move back, right? Move back so that move back from this domain to this domain using the Mobius transformation that sends this one to this one, so that this one is moved to this one, and then I can apply the one that sends this one here, and once I'm there, I can go back now, going from here to here. You see it? So somehow to compute the Mobius transformation that sends this one to this one, and I'm being careful with the orientation. What I'm saying is that this point at infinity goes to this point at infinity, this point at infinity goes to this point at infinity. So this goes to this oriented. And what I'm saying is that in order to realize this Mobius transformation as in terms of the generators, it's kind of I just move back through an orange one, and then go with a blue one, and then move back with the inverse of the original orange one. And that's what somehow my intention is. That you see how one can start expressing the Mobius transformations that start appearing and that one knows belong to the Fuchsian group in terms of the ones that I said are generators. Okay, and for instance, let's say I apply this one, and really what you are seeing here, you see the Mobius transformation that sends this one to this one actually should be, let me think, is the same. You see, am I? Yeah. So you see, like, if one wants to see that which Mobius transformation is the one that sends this one to this one, if you think about it, it's precisely the one that sends this one to this one. And it's actually a hyperbolic Mobius transformation. You see that somehow it sends this one to this one, and so somehow the repulsor sits somewhere here, and the attractor sits somewhere here. And so when I apply it once, kind of everything, like all the blocks move once, you see, towards the attractor. Okay, so that's one thing that I wanted to mention. Yeah. Okay, and then you see you can just start. Right, and then somehow by clicking and then seeing all these images of the original fundamental domain with the blue and orange boundaries, somehow what I want to illustrate is really that how you can really cover the whole hyperbolic plane with images of the closure of the original fundamental domain. Okay, so that's one thing. Yeah.
In the beginning, you said that there's always
Okay, so for the first one, yeah, actually, in a way, I actually cheated because somehow the way one sees that there is a Mobius transformation sending this side of this fundamental domain to this side is the way one shows it is precisely by saying, okay, notice this one comes from this one. You see, kind of just do that. You see like a conjugate the one that sends this one to this one by the transformation which under which you are computing the new fundamental domain. So somehow, I mean, what I'm saying is, so I somewhat somehow cheated you. You see, it's kind of, I said there is a Mobius transformation in the group that sends this one to this one, and then I told you like okay, and then one can see that that one belongs to the subgroup generated by the original two Mobius transformations by blah blah. But it's kind of somehow the way you show that there is a Mobius transformation in the group doing that is precisely by saying, okay, just conjugate.
okay. So,
you see, because you see what happened.
I actually was wondering why. So if you just take the first fundamental domain, which lies in the and why, when it is obvious, why should it be those two boundaries and why not those two, for example?
Right. Yeah. Okay. No. The second question I'm going to address in a minute.
I thought they were.
Yeah, that they are adjacent. Yeah. Yeah. So for the first one, let's see. I mean, I don't think it's a fully satisfactory answer, but somehow for the new fundamental domain, then you consider abstractly, without this conjugation trick or conjugation cheat, consider abstractly just the set of gammas in the Fuchsian group, such that, let's say this is our d prime, such that gamma of d prime intersects d prime. Oh, sorry, gamma of topological closure of d prime intersects topological closure of d prime. Yeah. That one again, we know that it has to generate the Fuchsian group, right? So yeah, but kind of what bothers me a bit is that we know it abstractly, and then I would really have to make an effort to say, okay, and then there is an element of gamma that really sends this whole thing onto this whole thing.
Okay.
And that can, yeah, I mean, it's possible to justify it, but it's kind of, to do it formally, it's a bit boring. Okay. Yeah, it's a bit, it's the sort of boredom that I was kind of mentioning that you see at the beginning of the class. But it can be done formally. Yeah. And then I wouldn't be cheating by saying, okay, and moreover, that one can be obtained by, you see, by just considering kind of the original one, the original blue one, and then just conjugating, because you see it's kind of, I'm going back to the original one and then performing the blue one and then coming back. So it's really a conjugation. Now for this, that here it looks like somehow the sides that are paired seem to be like kind of far away from each other, right? That's not always the case. So that's not a kind of, it's not a theorem that always happens. But before moving on, I just want to say something more. So, right. So now, since I know, I mean, I know that I haven't even, okay, I did tell you something about the Fuchsian group, which is, I at least told you these explicit Mobius transformations that belong to it, right? Kind of the blue one that sends this Euclidean middle point to the Euclidean middle point, blah blah. So I did tell you some concrete information about the specific Fuchsian group. Okay. But if you believe me that this is a fundamental domain of that Fuchsian group, and if you also believe me that this is actually a locally finite fundamental domain, for instance, if you believe me that it's a Dirichlet polygon for that Fuchsian group, then we know by one of the theorems we proved, with one of these proofs from kind of general topology that are not very transparent, but we know that we can that the orbit space H, I mean hyperbolic plane modulo the action of gamma, is homeomorphic to simply taking this blue fundamental domain, this blue ideal quadrilateral, and just gluing this blue side with this blue side, and this orange side with this orange side, where the gluing is dictated precisely by that Mobius transformation that I took. Right? So it's not just any way of gluing; it has to be glued along, you can glue only and precisely points that correspond to the Mobius that correspond to each other according to the Mobius transformations that they gave you at the beginning. And now, and if you think about that, then you have an idea of how the orbit space looks like, right? Because it really, the gluing instructions really look like those from a torus. If you think about it, it's really a torus, except that here there is one point here which is a point at infinity, which corresponds to this point at infinity, which corresponds to this point at infinity, which corresponds to this point at infinity, which is not part of the hyperbolic plane, and hence is not part of the orbit space. So the orbit space really looks like a torus with one hole, with one point removed from it, and that point removed from it, it's really a point at infinity. So if you think about it, the orbit space then looks like a torus with the surface is hyperbolic, and then a point at infinity. So okay, but so one thing that somehow I wanted you to see is that all that visualization is really due to the fact that we know that we can compute things just in terms of a locally finite fundamental domain, as long as it's locally finite. Okay, now let me move to another example. So let's see. So I want just 2 points at infinity. Yeah. And then here, so again, somehow what I have is, I know certain Fuchsian group that I'm not really giving you explicitly, right? Kind of, it's kind of behind the scenes. and it has certain elements which have this behavior similar to the previous one. So there are elements in my Fuchsian group that send this blue one to this blue one, and actually you see kind of this point at infinity goes to this point at infinity. This point at infinity goes to this point at infinity here. But also the blue Mobius transformation actually sends that point that you are seeing here. This point goes precisely to this point. Similar with this orange one, and similar with the pink one. So you see, for the pink one, this point at infinity here goes to this point at infinity here, and this point at infinity is fixed by the pink Mobius transformation, and it sends this point precisely to this point. Sorry, I did it. I switched order. Sorry, this one goes to this one. This one is fixed, and this one goes to this one. And so you see, then at least what I'm seeing here at least is that it is perfectly possible for two corresponding sides to be adjacent in the polygon. Okay, now since by construction I'm taking this one to be fixed by this Mobius transformation, what I automatically know is that Mobius transformation is going to be parabolic, and somehow I also know somehow the behavior on the iterations of that Mobius transformation, because you see, so the colors that I see are really different from the ones you see. Okay, sorry about that. Yeah. Okay. So I mean, this one is supposed to be pink. Okay. And now, so this one goes to, sorry. So this one goes to this one with orientation, and so you see, it's a parabolic one that has this behavior, and so its square has does this. So something that I can automatically see is that if I start applying the positive powers of that parabolic that sends this one to this one, somehow what I'm going to start seeing is copies of the blue fundamental domain, kind of going here, and somehow accumulating in kind of in the closed disk, accumulating towards this fixed point. So so somehow that's something that we can predict is going to happen. And then you see, so this is the image, and so on. And so on. And actually here, these black dots that you are seeing are actually the images. You see, I a priori fixed this point. If you want to, you can think about of that point as the W I start with for the computation of a Dirichlet polygon, and you can see somehow the images of that point under the iterations. So you see, so it really is kind of in sync with what we learned about parabolic Mobius transformations. And what you are seeing here is all of these are fundamental domains of the Fuchsian group. Right? And then I don't know, under the negative powers. So now things are going to move the other way, but in the end also converging to or accumulating towards the fixed point. not converging. Converging, I think it's a more accurate word, and so on. And you see, if everything that I said is correct, is true, you see, somehow it should be the case that that all these black dots lie on an Euclidean circle tangent to the unit circle in this fixed point. If everything that I said is really correct, right? So because they all should lie kind of in this circle stable under the integral powers of that parabolic. Okay, and now these other ones, I'm not justifying why it is the case, but these other ones are actually hyperbolic. So these other ones really have the other property of getting away from one of the fixed points and closer towards the other fixed point, which lives in the circle at infinity, and so on. And so on. Okay, now, okay. And now, of course, and again, kind of you can say, okay, there's the exercise, right? Okay, so the orbit space, what type of surface is it? And here you, and then you say, okay, so the easiest strategy is to say, okay, if you know that this is a locally finite fundamental domain, then just try to do the gluings or imagine the gluings, and then maybe you can answer, okay, it's maybe a torus with 1 point removed or whatever, right? And here, I mean, here it's really a torus with 2 points removed, because okay, so notice at least here in the fundamental domain, I have this point, which this fixed point, which doesn't correspond to any other point, at least in the fundamental domain. Yeah, in the closure of the in the closure in the closed unit disk, right, of the fundamental domain. Anyway, so this point at infinity is really not gamma congruent with any other point in on the fundamental domain. Yeah, I mean, I really have to say topological closure. It becomes a bit annoying to start to try to say things the right way. Okay, okay, but look at this point, for instance. This point corresponds to this point under the blue one, corresponds to this point under the orange one, corresponds to this point under the pink one, corresponds to this point under the blue one. Yeah, and sorry, you really don't see the same colors. Okay, I'm sorry about that. But you see, yeah, okay, yeah. But so you see, the other points, I can really trace. I can really see that all the other points are gamma congruent, right? So you see, at least in the fundamental domain, or you see in the topological closure, inside the topological closure of the Poincare disk in C, I really have like two classes, two kind of the set of points at infinity in the fundamental domain is that set is partitioned into two, right? One of them only has this point at infinity, and the other one has the remaining ones. So that should tell me that there is going to be 2 points at infinity, right? When I perform the gluing. Okay, and then let's say okay, so the gluing, how do I perform it? And then what I see is that this one and this one, they are really already configured as in a torus if I kind of ignore this part. But then let's say draw the geodesic, the shortest curve between these 2 points. So let me see if I can do it. Hopefully I can do it. Let me see. And then move it. Right. Okay. Yeah, and then so somehow so think about this. Cut the fundamental domain along this shortest curve, and then if you perform the gluing, it looks like a torus with one hole, and on this hole is this point is the point at infinity, this one, the one that corresponds to all of this, because the geodesic precisely passes through this to this. You see, so if you want to draw it, let me see if I can draw it maybe in the iPad. Yes, so let me. Oops, no, it's not here. It's here. Okay. So and the picture I have is more or less. So how is it? Is more or less. And here I have this geodesic that I'm cutting off, right?
Why can we cut it off? So we are looking at the module space, but there are points which.
So somehow what I'm thinking is the following. I'm thinking about trying to visualize the result of the gluing by cutting off, performing the gluings, and gluing back. I don't know, just because somehow I think that is a bit more convincing of why this is a torus with 2 points at infinity. But of course, yeah, I mean, of course, if there's some other way of just saying it, then of course that's better. But it's just, yeah. And then, yeah, so maybe so maybe I can just move it. Yeah, so okay, so more or less, right? And then you see this point at infinity is this point at infinity is gamma congruent, and then you see in one glues, let's say this way, and somehow the picture is like the picture of the gluing here, which is of course ignoring this part. What I would say is that it more or less looks like okay, so let's see. Okay, so what I'm going to do is just this would be like with the point at infinity. One second. yeah, it's something like here. So okay, so you see this is what I would draw for the previous example of the torus with one point at infinity. But here, I think I would somehow perform some cut like this. You see, and then cut that part. Is it clear? Is it more or less clear what I did?
So that point, this cut was the cut with the geodesic in the
Right. Yeah. 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 And well, and then an exercise would be, you see, to try to draw these ones. Which I'm not sure I can do live. I can do it live. I would think I have to think more a bit more about this. Okay, because then my point is that now to draw this part is easier. So you see this one, to just draw this part, it looks like at least the so over there I do have something like this that goes to infinity. You see, and that part corresponds to this, to just because I know that this has to be glued with this. You see, and then there is some point at infinity, like here, and then it's something like I cut something like this to the other point at infinity, and somehow in the end you have to glue this with this. And then you obtain this one point at infinity, which is this one, and then another point at infinity. Okay, now one thing. There is one thing which is deceiving about these pictures, and it's the following. So somehow the part about going to infinity is more or less accurate, but something which is really deceiving is this kind of finite part, because this drawing in terms of curvature is not valid at all, because here there are some points of positive curvature and some other points of zero curvature, if you think about it. Like if you think in terms of just just differential geometry of embedded surfaces in R3, here, for instance, here, points here they really are of positive curvature, if I'm not mistaken. And then there should be some others of zero curvature, I think, which are, I think, points here, I think, if I'm not mistaken. In any case, somehow metrically, this part, kind of the finite part of the drawing, is not accurate. Okay. 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 Now, what else? I need to say something more, which is the following. So here, it's kind of, this is the same picture, and here, as I said, I really how to say, in the fundamental domain, I really have two gamma congruence classes of vertices, namely these 5 here that you are seeing here, which are the ones that project to this point at infinity, and this other one, which is the one that projects to this point at infinity. And now something that I want you to notice is that since all of these points are gamma congruent, their stabilizers in gamma are all conjugate inside gamma. Do you see it? Because these points, so kind of forget about these quotients, forget about the orbit spaces, and think only about gamma acting on the Poincare disk union, the circle at infinity. And then what happens is that since these 5 points live in the same gamma orbit, right, because they are gamma congruent, you see, like for 2 of them, let's say that is kind of a Z0 and Z1, and that Z0, let's say that it's equal to gamma Z Z1, right? And then for some gamma in gamma, and then what? Then what I would say is that the stabilizer of the stabilizer of this one is what? Is probably gamma, the stabilizer of Z1, gamma inverse. Is this correct? Let's see. For instance, something here is of the form gamma, something that stabilizes Z1, let's say sigma, gamma inverse, right? And then I wanted to fix, is this correct? No, it's not correct, right? So I think it's the other way around. So let's see. The problem of doing things live. Okay, so gamma, Z0, gamma inverse. Okay, and so gamma, sigma, gamma inverse of Z1, yeah, this works, is gamma, sigma, and then this is just Z0, right? Z0. This is gamma of Z0, which is Z1. So this inclusion is correct.
Right? I think gamma to the -1 of Z0 is Z1, right? Isn't it the other way around? Apply the inverse of gamma to the equation, and I get gamma inverse.
No, you are right, but yeah, you are right. But notice Z1 is gamma of Z. I see. Yeah. So okay. Yeah, you are right. But let's see. And then this should work. Z1 is gamma of Z0. Gamma of Z0, and then this cancels, right? And then gamma inverse of gamma of Z0 cancels, and then only Z0 survives. And now it's fine, right? And then this shows this, right? So this conjugation fixes Z1, and then same reasoning shows the other one, right? Kind of just move things around. So okay, right. So of course, being in the same gamma orbit implies having stabilizers, having conjugate stabilizers with the conjugating inside gamma. And so coming back here, what you see is that all these 5 points have conjugate stabilizers, right? And those stabilizers, they are not conjugate to this. If they were conjugate, one would be able to kind of to cook up the other direction, right? That if they are conjugate inside gamma, then the points are gamma congruent. Okay. So this means that yeah, okay, so that's one property, easy to see. Sorry, you were not seeing everything. Okay, I'm sorry about that. Okay, and right, so that's one property. Another property, which now is less trivial, is that now pick any such point. Let's say this one that you are seeing here, and so the stabilizer, so the corresponding stabilizer, the non-identity elements, they are all parabolic, right? Because somehow they all fixed that point, which is a point at infinity. So they are all parabolic. Okay, so this is what is usually called the parabolic subgroup of the Fuchsian group. So a subgroup consisting entirely of parabolics, except for the identity, right, which is not assigned any type. Okay, but not only that, it's maximal with this property. So the stabilizer of any such point is a maximal parabolic subgroup. Now and then, as you can, and now, so for each vertex at infinity, I have a maximal parabolic subgroup, and for each gamma congruence class of vertices at infinity, I have a conjugacy class of maximal parabolic subgroups, and different gamma congruence classes. So this one versus this one give me different conjugacy classes of maximal parabolic subgroups. And theorem, they cover all. So the theorem, and it's not trivial, is there is a one-to-one correspondence. Well, there is a one-to-one correspondence. Between conjugacy classes, and of course with the conjugating transformation belonging to gamma, so gamma conjugacy classes, right? I mean, that as opposed to conjugating inside PSL2R. That's what I mean. So gamma conjugacy classes of maximal parabolic subgroups of gamma with gamma congruence classes of let's say parabolic fixed points, let's say parabolic vertices of D, let's say. And if you want to think that D is a Dirichlet polygon, that's fine. So it's not trivial because one has to show you see kind of the correspondence. It's easy to see what the correspondence should be, and it's any such point corresponds the conjugacy class of its stabilizer. And then what is not trivial is to show that they are maximal parabolic. You know, yeah.
What does
that that there is no parabolic subgroup of gamma properly containing the stabilizer. That's what it means. And so this that it's maximal parabolic is not trivial, and not trivial also that actually if you take any maximal parabolic subgroup, is conjugate to one of these stabilizers. That's also not trivial, because you see, for instance, apply this transformation, and you automatically get this other parabolic fixed point, which was not taken into account here. So you see here, when you take the stabilizer of this point in gamma, that's another maximal parabolic subgroup. Conjugate to this maximal parabolic subgroup precisely by the Mobius transformation that I applied, right? But the point is for any point at infinity which is fixed by some element of gamma. I mean, but for any parabolic fixed point, you can say that it's conjugate to one of these, and that's not trivial. That's yeah.
I'm sorry, I lost the thought with regards to the maximal parabolic subgroups. So we say a subgroup is parabolic.
Mm-hmm. One has to be a bit careful, because, for instance, if for instance this Mobius transformation, that one also has a fixed point, but it has two fixed points. I mean, this Mobius transformation is hyperbolic. It has two fixed points, and so somehow when I consider those two fixed points, stabilizer, yeah, I don't call it parabolic subgroup. I mean, its non-identity elements are not parabolic.
Yeah, right.
Yeah.
Then one can say it's maximal if there are no other
Parabolic
functions which I could add to.
Yeah,
to the
yeah.
group.
Yeah, yeah. Let me see. Okay. Let me see, because maybe what is confusing you is that it should be obvious. Let me see, because I take, you say take the stabilizer of one of these points.
Yeah.
That stabilizer has to be a parabolic subgroup. And then once it's parabolic subgroup, because since you are defining it as the stabilizer, it has to be maximal. Yeah, okay, so maximality is clear. Yeah. And yeah. And then what is not clear is that if you take any point at infinity fixed by some parabolic, then the stabilizer is congruent to one of these, to the stabilizer of one of these.
So that would be the left-hand side.
Yeah, that everything here corresponds to something here, right? So if you want that this is surjective. Right. Okay. Now, let me move on, because somehow so far what we've seen is kind of, we are only seeing kind of nice pictures. This is still kind of what I would call a nice picture. But I'm going to, yeah, but there are some pictures that are actually not so nice. All right, so here, same kind of thing, right? This corresponds to this. This one corresponds to this one on the Mobius transformations that, see, this point goes to exactly this point, so on. And now here you have a kind of just a half geodesic, right? I mean, it's kind of what's the actual difference between this and this? That this one really is kind of complete or doubly infinite, right? But this one is only like infinite in one direction. Okay, now here the Mobius transformation, you see here, as soon as I say that, as soon as I impose the condition that this half geodesic goes to this half geodesic, the Mobius transformation is automatically determined. What I'm trying to say is the following: for this blue geodesic and this blue geodesic, to actually determine a Mobius transformation sending one to the other, I have to say, okay, not only this point goes to this point and this point goes to this point, I really have to say some finite point, and I have to tell you to which point I want to send it. Here, when I say I want this one to correspond to this one, well, first of all, this finite point has to go to itself. This infinite point has to go to itself. But I don't have the choice of, like some finite point here. I cannot choose to which point send it. In contrast to the freedom I had here. Why do I not have that freedom? It's because, you see, I know that this point goes to itself, and then let's move, I don't know, let's move in 1 unit, right? So the distance 1 from here, and so let's say that I'm here, and then the image of this one has to be 1 unit away from this point. The point is, this is finite, and it has to be an isometry. So really, just saying that this one goes to this one determines everything, determines the whole Mobius transformation. In contrast to the other, where I have one level of freedom. Okay, and also in contrast, you see. Let me draw again the previous one. Also in contrast to this one, because here, you see, it's very similar. Here, this one is a fixed point, and I'm sending this one to this one, but this one is a point at infinity. So I cannot say, like, okay, move 1 unit away. There's no such thing. And so for this point, I can choose to which point here it goes, and in order to determine a Mobius transformation sending the whole thing to the whole thing. Okay, but let me go back to the other picture. All right, and now here you see. Here, let's take this point at infinity. So it corresponds to this one under the blue transformation, which corresponds to this one under this, what I see as orange transformation, which corresponds to this one under this one that I see as a pink transformation, which corresponds to this one under this blue one. And then I close the whole cycle. You see, I mean, I exhausted all the vertices at infinity in the process. So what I see is that there's again only one point at infinity, and somehow there is this point. You see, it's fixed by an element of the Fuchsian group. So it's an elliptic fixed point of the Fuchsian group. And then in the quotient, I have to, in the orbit space, I have to identify this one with this one. And then, yeah, then it becomes a singular point, or if you want, you see, we know that the orbit space admits a Riemann surface structure for which the projection from the hyperbolic plane to the orbit space is holomorphic. I mean, we stated it without proof. I mean, without proof when there are elliptic fixed points, because the proof when there are no elliptic fixed points is not so hard. And with respect to that holomorph, with respect to that Riemann surface structure of the orbit space, this point becomes a ramification point. So you just like yeah, I don't know if you've taken courses on Riemann surfaces, but that's precisely what happens. Okay, so it's a ramification point, and the index of ramification turns out to be precisely the order of the stabilizer. But okay, but anyway, right. And now what happens is the same. You see the same game that happened here for parabolic fixed points and conjugacy classes of maximal parabolic subgroups is again true for these elliptic fixed points. So there is an elliptic version of this theorem, that is that there is a one-to-one correspondence between gamma conjugacy classes of maximal elliptic subgroups of gamma and gamma congruence classes of elliptic elliptic vertices of D, which would be, by definition, would be points in D bar, points in D bar that are elliptic fixed points. Okay, now maybe to start wrapping things around for today. Let me say a little bit about Poincaré's polygon theorem. Yeah, no, okay, no, before that, let me do some clicks. Okay, so here you see this is order 4. And this is the 4 that I use. That 4 is this 4. And then let's say that I apply this one, and then I obtain another elliptic fixed point, and then here again 1, 2, 3, 4. If everything is correct, you see these 1, 2, 3, 4 black dots should actually lie on a hyperbolic circle with this hyperbolic center. If you see, like, even if my program is correct and everything. Yeah, and of course, you see, like, parabolics and elliptics can live together. So let's see this, and then let's say 8, and then also like greater genes, let's say. Okay, and now this looks a bit crazier, but you see, like this one here, I have a parabolic, and then what did I do? No, that's not a parabolic. I'm sorry, that's not a parabolic, because you see that somehow this one really is paired with this one. not with the adjacent one. So where is there some? Here is some parabolic. Here, etc. And then you can see that I start also producing some more elliptic fixed points. And then here I can also, etc. Right? And then here some other elliptic fixed point. And so on. Okay, now let me just say one thing about some not so nice pictures. I mean, that really the theory can become more complicated. And in a way, I find it a bit unfortunate, but because it may happen, you see, something that does happen is that, let's say, consider this shortest curve, and now let's say this one, and I don't know, this one, and then of course then I can send this one to this one, this one to this one, this one to this one, and let's say some point there, and I can choose a point here, and then there's definitely a Mobius transformation in SU11 doing that, and similarly this to this, this to this, and this point, let's say, to this point, and there's definitely Mobius transformation preserving the Poincare disks bijectively and with that behavior. Things still look like a kind of, I think, I mean, this, yeah, one can show that what I just did actually produces a Fuchsian group. Actually, something funny is that it's easier to show that what I just did produces a Fuchsian group than in the figures that I showed here by Poincaré's polygon theorem. But okay, but the not so nice part is, you see, now when you perform the gluing, you have this whole segment at infinity, this. So somehow the picture is a torus with one hole, but that hole is a whole kind of funnel at infinity. So somehow the picture is like that, but all these points are really points at infinity. And then okay, and this is kind of still, it may still qualify as nice. Kind of when it becomes not so nice is when really you start having these sort of intervals at infinity, but also the other type of points at infinity, which are just for the parabolic ones. And if instead of the picture, what you are given is just the Fuchsian group, it may be hard to locate, to decide. You see, you have a point at infinity, and then to decide which type of point it is. A point that lies in a kind of in an interval at infinity of the fundamental domain, or a point which is a parabolic fixed point. You see, kind of things can become complicated. Okay, and then now kind of just to close, saying some words about Poincaré's polygon theorem, which is by no means easy to prove. And let's say it's the following. So let me go back to the easy situation. So when I do this, you see, I mean, I have 1, 1, 4, and then somehow when I give the computer this information, what I'm telling the computer is, okay, I want my Fuchsian group. I want a specific Fuchsian group so that in the quotient the genus is 1. There is exactly 1 point at infinity, or if you want in the Fuchsian group, I want it to have exactly 1 conjugacy class of maximal parabolic subgroups, and I want it to have exactly 1 conjugacy class of maximal elliptic subgroups, and any such elliptic subgroup in that conjugacy class I want it to have order 4. So it's kind of all of this, and then the program is written in such a way that it doesn't compute kind of randomly a Fuchsian group with that property. So somehow I wrote down a program where what the program does, all it does is it only computes the Mobius transformations that you see. You see, here you are seeing somehow this. Well, I see it as orange. Yeah. And then my program in the background, it really computes 1 Mobius transformation sending this point to this point, right? For the blue one correspondingly, and for the pink one even more, right? I mean, for the pink one, I know that it's completely determined by just saying this fixed point and sending this one to this one. So it computes the inverses. Right? So it computes 1, 2, 3 and their inverses, so 6 Mobius transformations, and that's all it does. That's all it does. And what I know is that the subgroup of PSU11 that these 6 Mobius transformations generate is Fuchsian. I know that. I'm absolutely sure of that. And I know that also the blue region that you are seeing is a fundamental domain. And the reason why I know that is Poincaré's polygon theorem. So what super roughly speaking, what Poincaré's polygon theorem says is, suppose you have a convex hyperbolic polygon with an even number of sides. There's a caveat there, but maybe I'm just going to let it slide. So suppose you have a convex hyperbolic polygon with an even number of sides, and that the sides are paired, but not only combinatorially, kind of I tell you not only how, that this side corresponds to this one, they are paired also geometrically. That is, I exhibit a specific Mobius transformation sending this one to this one. So it's not only a combinatorial pairing; it's a geometric pairing. Okay, and what the Poincaré polygon theorem says is, okay, starting from that, then you have some set of generators from which you consider the subgroup of PSU11 or PSL2R they generate. And then Poincaré's polygon theorem says, if 2 conditions happen, then the subgroup generated by the Mobius transformations that you gave me is Fuchsian, and the hyperbolic polygon you gave me is a fundamental domain for that Fuchsian group. And these 2 conditions are the so-called parabolic cycle condition and elliptic cycle condition. Now let me kind of, just to finish, because I'm about to run out of time, let me maybe say something about the elliptic cycle condition. So you see, throughout the lecture, I was talking about, you see, the intersection of a gamma orbit with, and here instead of D, I denoted it P. So P is my polygon. Right. So I talked about these gamma congruence classes of the vertices. Right. So it's kind of really what I did was intersect gamma orbits with this closure. Okay. Right, and then if I intersect any gamma orbit with my polygon or with its closure, of course, since in the intersection of I take the intersection of any such gamma orbit with p bar, okay, and then for all the elements in that intersection, well, they are in the same gamma orbit, so their stabilizers are conjugate in gamma, so they all have the same order. So they all have the same order. And now what I look, so you see, let's see, I draw. Let me see. So let me draw kind of my polygon. When I draw my polygon, somehow I have somehow what I'm drawing there is here I'm drawing just here, these are just the intersection of a gamma orbit with p bar, right? So these points are really gamma congruent, and they are vertices of the polygon, and so here the polygon is here, right? And somehow here it continues like and of course for each of those vertices, each of them subtends some angle for the polygon, and these angles are not necessarily the same. Okay, but then the angle sum of the whole thing is defined to be just the sum of these angles. For instance, in these pictures that I drew, somehow really, for instance, here you have only one point. So this is the whole sum. So this angle really is this whole sum, this angle sum. But that's just because somehow my program computes a polygon where each of these elliptic fixed points is not gamma congruent to any other elliptic fixed point in that polygon that I draw. Okay, but anyway, and what one proves is this identity. So if you take this angle sum, so if you take the sum of these angles for elliptic fixed points in the same gamma orbit, elliptic vertices in the same gamma orbit, elliptic vertices of P in the same gamma orbit, if you add all these angles, that sum of angles times the order of the order of the stabilizer of any of the points, which is a maximal elliptic subgroup, is 2 pi. And so that is if you know that this is a Fuchsian group, this has to be satisfied. Yeah.
Just the gamma orbit is discrete, and
Right, yeah.
that, and the intersection with p bar would be finite, and now I want to define an angle of finitely many points. Do I just like take the geodetic?
No, yeah, angle sum. So for each elliptic vertex, and by that I mean an elliptic fixed point which is vertex of your fundamental domain. For each of them, you measure the angle, the corresponding angle.
But isn't my gamma cycle just a set of points?
Yes. Right, but it's a vertex, right? So it's kind of so you,
so of p, and then we
yes,
look back at p.
right,
okay.
yeah. So the fundamental domain here sits here.
Right. Okay.
Yeah. So it's kind of this is a convex hyperbolic polygon. Yeah, and then at each vertex, then kind of I look at P, right, and then I measure.
Right.
Yeah. And then there's this theorem, which is if if your Fuchsian group if your group was Fuchsian, and this one was a fundamental domain, then this equality has to be satisfied. So thinking backwards, that tells you, so that tells you that if you start with a polygon and Mobius and the pairings and the geometric pairings, which are these Mobius transformations, I mean, first of all, if you really want to generate a Fuchsian group, so a discrete subgroup, like first of all, this condition has to be satisfied for the elliptic fixed points that lie in the, like for the finite vertices of your polygon. So it's not like everything will work. That's my point. Okay. So there's this condition, and then there's another which is which has to do with the parabolics. This I'm not going to mention explicitly. And what the Poincare polygon theorem, roughly speaking, says is, well, somehow, if now starting backwards, starting only with your polygon and with the original set of Mobius transformations, if this is satisfied and some other condition is satisfied, this parabolic cycle condition, then your group is Fuchsian. Your group is discrete. And your polygon is a fundamental domain for that subgroup. And that's the reason why I know that, you see, what I generate here is going to be Fuchsian with this fundamental domain.
It also has to be locally finite then automatically, since it's the
Poincare. Right. Yeah. No. One has to check. Yeah. That I see what you are saying. Yeah, this I would have to check whether this is. This I have to check whether this is also asserted by Poincaré's polygon theorem. Yeah, this I don't have it on top of my head.
I mean, if the polygon is the Poincaré polygon, we would.
Then you know. Yeah. This I have to check. Yeah. Okay, but so kind of to summarize, what the Poincaré polygon theorem says is, okay, as long as you satisfy certain somewhat technical numerical conditions, you can start producing Fuchsian groups with certain desired behavior. Okay, and then let's leave it there. So I'll see you on Monday.